Alright, we're going to continue working with simple harmonic motion, but particularly relating to a spring system. So let's see if I can get this going. I've had a little bit of problems today with this. So we have a spring. And now, so the spring at the moment is stretched. This is the same spring compressed together. And somewhere halfway in between those two situations is an equilibrium position where if there's no energy whatsoever in the system, it would just relax and rest at that point. Now we know that the equation, that the acceleration at any given point in that curve is equal to minus omega squared x. Hooke's law, which we have done before, talks about the tension, talks about the force being equal to the spring constant x times the displacement x as well. Now it's not quite true. In fact, if we look at this in a slightly different way, and we're thinking it from the perspective of the tension in the spring, when the spring is, let's get that equilibrium position drawn here. Just change colors. We have our amplitude here and the amplitude here. When it's up here, when we're at this position here, the force is actually pulling downwards, but it's actually pulling in the opposite direction. Down here, it's pulling upwards. So we've actually defined the displacement as being this distance here in Hooke's law. Now that's okay if we just think of the force as being the weight. That's just the weight. However, if you think of it as the force being the tension in the spring, so if we call the tension in the spring, let's call it T in the spring, it's actually not Kx, it is in the opposite direction, it's minus Kx. So let's just keep that in our minds just for a little time as we go forward. Newton's second law says that that force, the tension, is equal to mass times the acceleration. So setting these two equations and equating to each other using A as the common factor, so that tension, and also using the tension in the spring as minus Kx, what we'll find is that acceleration is equal to minus K over mx. The next little magical step occurs here, because if the acceleration equals to minus k over m times x, and the acceleration is also equal to minus omega squared x, we could write the acceleration is equal to, as we've seen already, minus omega squared x. Therefore, omega squared is equal to k over m. From our circular motion equations, we know that omega is equal to 2 pi f, and we know that f is equal to 1 over t, and therefore we can actually set, so we know omega is equal to 2 pi over t, and if we square that, that's 4 pi squared over t squared. If we, so this t is the period of oscillation. This S is the frequency of that oscillation. In hertz. Now, if we combine this equation here with combine that equation with this one, we get 4 pi squared over t squared is k over m, or as a parallel calculation, which we'll do over here, 4 pi squared f squared is equal to k over m. Now, in a simple harmonic motion, and of course we're using this specifically for springs acting under gravity, we'll have to do these calculations again if it was something to do with, say, penduli or springs working in tandem on a horizontal surface. We can actually work out what the period or the frequency would be. So if we rearrange the equation here on the left hand side and satisfy yourself that this is correct, we end up with t squared equals 4 pi squared m over k. If we want to say make t the subject, take the root out of both sides, we get 2 pi root out of m over k. Similarly, if we do the same for the frequency on the right hand side here, I'll do that in a different color. If I want the frequency, it will be equal to, taking the root, satisfy yourselves again that this is true by doing the rearrangements, getting used to these kind of things in your own case. K over m. Let's just look at this very quickly and just see what the impact here is. Remember what K is. K is the spring constant. So the stiffer the spring constant, the higher the frequency. The lower mass, higher frequency. And of course the opposite is going to be true over here, that the higher the mass, slower period. And the higher K, also slower period. Right, one of the practicals that we're going to do, you're going to be asked to plot t squared against either a mass or a spring constant. Now it's more difficult to vary the spring constant, so it's going to be against the mass. And because you do a graph of t squared, on this axis here we have mass in kilograms. We should get a straight line where the gradient take the equation that we have down here, gradient would be (4 pi squared over k). Interestingly enough, one of the questions that one can always pose to students is how you'd measure mass out in space. Now, out in space, of course, we don't have weight, but we do have this equation where we relate mass to a period. So if we have a spring system, and we could have maybe two springs working at opposite ends here, you satisfy yourself what the maths is behind this. If we have an object and it's oscillating across like this, at one point it's being pulled by this one and pushed by this one on the opposite way around, you get a very similar equation. I'm not going to go into deriving that equation, but you could probably see that t squared is somehow related to some constant, call it little g, times the mass. Now if we know what the spring constants are on both sides, if that happens to be something like 4 pi squared over k, all we need to do, as long as we know what this is, of course these are just constants, if we can measure the time and the period of oscillation, we can work out the mass. And this in fact is a very similar system to what they use on the International Space Station to measure people's mass. Because of course what we're doing when we're measuring, if we're using scales on a planet, is inside the scale there is a spring that's being compressed. And that compression is using Hooke's law and telling us what the weight is based on the displacement that the spring has experienced to tell us what our weight is, not what our mass is. If we move that set of scales to a different planet, we will get a different value. However, using some kind of spring system, a bit like this one here, we can actually work out what the mass is of a person that's actually sat in space without having to go through understanding their weight. And as such, this is actually a very useful way of understanding reality and how masses work. Another typical way of doing it is by having a set of scales, a known mass on this side and an unknown mass on this side, and then constantly adding this. But this still demands that we have a weight pull, that this is causing a pull in this direction, so that there's a pull in this direction. So you're still relying on gravity for something like this to work. However, in this case here, we're creating artificial forces that are storing energy in elastic potential energy, and we can actually use that periodic knowledge to actually understand what is actually going on in terms of the maths. This is a practical that you'll be doing very soon.